awake and ready for a nice, deep technical talk? I hope you've all had your coffee.
Yeah.
Steve is going to drive us through more information about the guarded control stack. Go.
Thank you, Steve. So hi, folks. You know me from last time. Steve Capo. I work in the distros team at ARM, and it is lovely having you all round for the Debian MiniDebConf. Today, I'm going to talk about some more architecture. Those that remember last year will remember I talked about pointer authentication and branch target identifiers as security features. Last year, I gave a sneak peek at guarded control stack, which was another security architecture, which can also be used for profiling. So we call it FEATS GCS in ARM speak on the websites and everything. It is optional from ARM 9.3. We are not going to target Trixie with this, so I won't get things thrown at me by going through it now, because it involves some toolchain changes. We'll be going for Forky, which is, I think, the one after. For today, I'm going to briefly talk about the architecture, just so people get familiarity of what it is and why we're keen on putting it on. There's a lot more documentation in the references section to go in really deep to use it. We're enabling FEATS GCS upstream now. There's a few of us working on it. So some of the bits are still yet to be merged. And I should have said this last year as a content warning. This talk does contain some assembler, so apologies. So let's go through the architecture quickly. So on the left-hand side here is an amazing C program written by myself. The idea behind the C program on the left-hand side is to demonstrate control flow. So we start at the bottom with the main function, the entry point. We call the hello function. The hello function prints out hello. It calls the world function, which then prints out world. We return, print the end of line character, return 0. On the left-hand side is the C code. On the right-hand side is some slightly simplified assembler, but the right-hand side is pretty much what we get when we compile this program. Now, the reason I'm talking about the assembler is it's easier to see some of the concepts when looking at assembler that I'm going to talk about for FEATS GCS. So the control flow, predominantly we're going to hello, then we're going to world, then we're going back to hello, then we're going back to main. The way we do that in assembler in ARM is we have this thing called link register, which is highlighted in bold. That's basically your return address. When I return from a function, I go to the link register. The salient points on the right-hand side is that I'm storing this into the stack. I'm popping it from the stack as well. There's some other stuff in the background, but it's pretty standard assembler with BL, branch with link, calling a function, return, returning from a function. The big point on the slide is the fact that these X30s are going into the stack and back from the stack. So we're putting that. This is similar on x86 and other architectures as well. We store the return address on the stack sometimes. So I talked about this a bit last year as well. If we put the return address on the stack, that's open for manipulation by somebody doing something nefarious. So the control flow can be attacked. PAC and BTI that I talked about in the previous MiniConf talk do address return-oriented and jump-oriented programming style attacks. The other thing about this thing, about storing the return address in the stack, is it's an absolute pain in the backside to get a list of return addresses. So if one is doing, let's say, profiling and optimization, it's quite commonplace with a profiler to take the call stack and say, okay, at the sample point here, this is what led to the point where I'm sampling. So taking the call stack is done quite a lot for profiling. Now, when we mix different languages, and indeed the assembler I showed in the previous slide isn't the full story. We've got these things called call frame information directives, which are lovely things, which I've spared you from today. But when we mix languages, when we have quite deep call paths, getting all the call stack information does take time as well as being fiddly. So if we're doing that a lot of times, it can be expensive as well for profiling. So the guarded control stack is not just a security thing, it's actually really useful for profiling as well, because it puts all the call frame information into its own area. So the easiest way to get the concept is just to have a look at it when we use feat GCS. So I've taken the same assembler example and highlighted some colours, and I've put a notifier on the right hand side. So in this example, let's say we've placed a breakpoint in the world function and we've executed, we stop at the breakpoint. So we're at the yellow at the very top. So we got to the yellow from just above the orange in the middle, and we got there from just above the blue and the bottom. So what GCS does is it takes this information and puts it in a nice little memory table for us automatically. So when we look at this particular register, we can see the return address is all in a nice, neat, contained place. So more formally, when we activate feat GCS, it subtly changes how some of the instructions work. So I mentioned the BL, the branch link, the sort of call instruction. That does an extra thing. So when feat GCS is enabled, the branch link actually takes the return address and pushes it onto this special area of memory. And when we do a return instruction, the return address looks at the special area of memory, checks to see it matches the link register, and then pops it and returns if it matches. The special area of memory as well here can be read quite easily by user space, not a problem, but writing to this, there are a set of restrictions, so it can only easily be written to normally by a branch with link instruction automatically. So it's hard to tamper with this easily. So the idea is, not only is there an accessible call frame that's given to us for free, that's useful for profiling, there's a little bit of security on there as well to prevent sort of either accidental or malicious manipulation of the call frame. I've gone over that very vaguely. There is the ARM architecture reference manual, which goes through it correctly and formally, but this is the gist of what we're trying to do, and this is why we're interested in the architectural feature. So how do I make it go? So I'll go through this bit slowly because I'll go through a summary of what we've been doing so far with architectural features in Debian. So last year we talked about pointer authentication. So pointer authentication, we had special code sequences that we were baking into user space, and indeed it's in the kernel as well. And pointer authentication is enabled by default, and it's self-contained as well. Now, one can disable pointer authentication. The end user can do it globally via a kernel command line, so they can say off, and it will deactivate. Branch target identifiers were slightly more sophisticated because branch target identifiers involved calling across different functions. They weren't self-contained as pointer authentication was. So with branch target identifiers, we had to mark each binary and say, this is BTI compatible. And in order for a binary to be marked as BTI compatible, all the execution units at link time had to advertise that they were also BTI compatible. So the idea was, as the software was ported over to enable BTI, the only issues with BTI were things like assembler sequences. Then again, it would be enabled by default once the executable advertised that it was enabled. One could disable BTI globally, again with a kernel command line. With guarded control stack, we don't actually have too many changes in user space. There's a few things that change, but we still need to have some level of annotation to tell the system that this is compliant with GCS, please load it. But one really important thing about this architectural feature, which should make it hopefully easier for us to justify getting in, is it's an opt-in mechanism. So somebody has to actually set an environment variable, a glibc tunable, that says, please use GCS if you can. And the idea behind this is we can enable it reasonably aggressively, but there's no risk to the end user because there's minimal change in code. Pretty much, I'll go through the bits that do change, but it's mainly just binary annotation. And the end user has to switch it on for it to actually have any noticeable effect on them. So it's hopefully that makes it easy for us to justify getting it on in more places earlier. So running a program with feat GCS is, we have to enable this tunable. So as I mentioned before, we're still upstreaming most of this, so this stuff's still being discussed. So the precise naming may vary, but the concepts should remain the same. On top left here we have a command line with a glibc tunables environment variable, and I'm running my hello executable. Now what happens is the C runtime loader, the dynamic loader, will pick up the fact that the tunable's enabled, and it will perform some checks on whether or not the executable is marked. And the runtime loader will ask the kernel, please enable GCS for this process, or for this thread of execution that's going on. The tunables are reasonably simple. The high level one is switch it on, switch it off. And then there's a more fine-grained sort of policy we can set that can aid for debugging, where we can switch it on completely. We can switch it on and actually make it slam the brakes on if it detects a condition that's invalid, such as opening a shared library that's incompatible, or even if any binaries are marked incompatible, throw an error as well. So this can be enabled by the end user. By default, GCS is off. The execution flow is the same as if we not enabled GCS at all. So there shouldn't be any noticeable effect on the end user. So in order to test all this, I'm going to mention this in passing because it might be of interest for folks who are interested in following what we've been doing as a team to enable it. So this bit isn't quite Debian, I'm afraid, sorry. But we've had changes to the glibc, to the kernel, to the compiler, to GDB as well, and probably some other bits I've forgotten. The idea to get all these working together with binary annotations, we need to rebuild everything to test it. Part of my team work on Yocto project, so we've got a Yocto project test layer. The nice thing about this particular link here is it is literally one line to make it and then one line to execute it. It does everything, downloads everything, executes everything. Whether or not you've got an x86 system or an ARM system, it will just run if you want it to. For the curious, for the testing, we're using the fixed virtual platform. That's basically a model developed by ARM internally, but it's released for people to just load and run. So that's available at the link as well for those that want to know the models. But that's done automatically by the layer. Now, more importantly, let's get this in Debian. So to get this into Debian, we need to annotate binaries for guarded control stack. And we do that in the exact same way we have been doing for Trixie for PAC and BTI. We use the M-branch protection equals standard. So that flag, when GCC version X comes out, will automatically also annotate binaries for GCS and do a few extra things needed for GCS as well. So the standard build system flags and everything should naturally just start switching GCS on as the toolchain gets upgraded in Debian. So that's why I'm thinking probably post-Trixie, because I think it's GCC 14 in Trixie, if I remember correctly. And again, we can just read ELF and see a GCS flag enabled. There are some flags as well for bug hunting to see why isn't GCS enabled that will spit out build errors, but those flags are still, as can be seen from the name, experimental. Those flags are still being figured out, but there will be flags people can use to test this as well if they're porting it over. It's probably going to be mainly my team doing it, but if you see us doing stuff with that, you'll know why. So I'm going to mention one bit about GCS extra that's kind of interesting. So to reassure people that might be involved in dealing with low-level libraries that could potentially need more sophisticated modification for GCS. So the guarded control stack protects against the control stack being manipulated. So if we want to actually manipulate the control stack, there are a few cases where we want to do that, and for good reasons. So things like long jump, set jump, for example, you need to modify the control stack. So certain library routines will need to be changed, and indeed glibc's got some changes, GCC's got some changes as well. Things like goto label in GCC, there's logic in there for GCS so it doesn't catch fire. Now, let's say somebody's got a particular library they're doing, maintaining. There is a kernel API to see what the GCS status is. Now, sometimes when one is writing really low-level code, a syscall is not something one can do. If they're really low into a signal or something like that, they don't want to make matters worse with a a syscall. So very interestingly for GCS is we've got a special instruction called check feat, and this tells software that GCS is running. Now the cool thing about this instruction is you can run this instruction on all the older ARM cores as well, and it will behave in a way to tell you that GCS is disabled. So we have a code sequence from the ARM architecture reference manual on the right hand side. So if anyone is genuinely worried about how to implement such a scary thing with control flow, there is at least a very nice detection mechanism that's used to make life a bit easier. But I thought I'd signpost that because that's a very new instruction that's come out with the GCS. And it does make life a lot easier to write some code for detection. So enabling GCS and assembler, as I said before last year, the first rule of assembler is don't use assembler, it's horrible. If you can get rid of assembler, please do. There are tools to make assembler better than we can. However, for some people that's not a luxury we can have. At the moment, we're still going through the fine detail for the ABI for the objects, but it's looking very similar at the moment to the way we do it for PAC and BTI. We've got this special note property we can put in places. Eagle-eyed people will see this in some upstream libraries already, and basically it's an extra bit set in there to signify to the assembler that yes, this assembler file is this execution unit produced by the assembler will support GCS. So the current status, there's upstream support underway for the kernel, bin utils, GCC, glibc and GDB. It's already in LLVM18, GCS support with the branch protection equals standard. Our strategy for Forky was to put up a wiki page on GCS explaining what on earth it is and go through some of the stuff in this talk. When GCC gets the support, the branch protection equals standard stuff that we've already got in Trixie will start enabling GCS for the next distro, the next stable. Once glibc has GCS support, it should just be a case of bringing in the new glibc, which will probably happen anyway. And again, for the kernel, we'll keep an eye on it because at the moment, there's a kconfig incompatibility of uprobes, but I suspect that'll be addressed. That's not a biggie. But when GCS is in the kernel, we'll make sure it's enabled in kconfig. And we'll do basically what we've been doing with PAC and BTI. We'll just be going on a bug hunt upstream, my team and others. It's basically finding stragglers and enabling the tech where it's needed. So I was going to just draw everyone to one more thing because I've locked everyone in a room again. I'm going to remind everyone that we are recruiting at ARM. We're recruiting for a lot of roles. There are hardware roles as well, but I don't know anything about hardware, so I can't list what we're doing. However, if anyone is interested in any role at ARM, please do talk to me. Or if they know anyone interested, please do talk to me. And I'm happy to try and connect people up and give advice and again, give honest feedback as well. I've been at ARM for 12 years, so I think it's a reasonable place to work. But if anyone wants to know any more, please grab me. Now I've finished with the spam. I'm happy to invite any technical questions on GCS. Right. So.
Yeah, thanks for that. Thanks for that. Yeah, I have two questions. The first is it possible, if you have a library that doesn't support GCS, then does that mean that the whole executable doesn't?
Yeah, so the way it works is GCS is enabled in the execution context of the current thread, and subsequent threads are automatically created with GCS enabled as well. So the problem with external libraries is that they share the same execution context, so there would be an incompatibility there. So that's why we've got this bad boy here, to basically force a crash immediately with informative information as to why. But yeah, so that's why it's a very conservative policy to opt in. So, yeah.
So the second question is, if you have this secure stack with all your your back pointers, why do you still need the link pointer? Why do you need to still store?
It's a good question. So, sorry, Mark's got his hand up. Go for it, mate. Do you want a microphone? Yeah. Yeah. Mark knows more than me. He's doing it in the kernel.
Yes.
So you don't, and it's actually optional in the architecture. However, if anything does any unwinding, then existing programs will obviously not know about GCS and will try and unwind using the link register and the stuff on the call stack. So so the architecture has the support for maintaining both simultaneously, and in Linux we've left that on because compatibility. At some point we might go in and provide an option to turn it off, but it's like one extra memory load and store per function call, and the compatibility benefits outweigh the small overhead.
Yeah. Also, it's usually stored as part of a pair as well, isn't it? So the frame pointer is usually done anyway at the same time. So this is from the compiler. So yeah. Thank you, Mark.
So you talked about enablement, and I think you have a slightly odd definition of end user. So as you know, ARM chips are often used in phones, and you said the end user would enable this glibc tunable. So I'm imagining a page in my Android settings.
Oh no, this is for, it's a good point though.
So no, my point is, like, presumably you're intending this to be enabled by default at some point.
Yeah. So for Android, there's a slightly different strategy to switch it on. But yeah, it's the idea about this is to let people have control over it. So for example, there could be a daemon or something with a very small footprint that people would like to throw extra layers of protection on, and they know it's safe, and they go, okay, we'll do it. But yeah, hopefully, as it gains, we probably could. We've got a very similar mechanism for memory tagging extension, which is another thing that checks malloc and free in glibc as well. But yeah, that's up to the community how to switch it on. Hey, Wiki.
Hello. So I packaged libbacktrace recently, whose job is to unwind call stack. So it should probably do something different for this. And I guess the question is whether, I mean, it'll still work, right?
Yeah,
using the existing thing.
Yeah,
So we don't have to do anything. But there's an interesting question of what is the right thing. I guess it should, if GCS is available, it should go and look in the other.
That would be a good thing to do.
The checked stuff. It's an interesting question. Is like whether it should check if they're the same. I'm not quite sure exactly how much. Whether it does anything more than unwinding and showing you the things, or if it's supposed to check stuff.
So if depending upon the exact unwind library and what it's doing, so let's say LinuxPerf, for example, the tool, that's predominantly interested in getting the call frame information and not much else. For that, it's reasonably easy to do, I think, a ptrace or whatever to inspect the GCS state of the process, pull out this pointer here that can be queried quite easily with an API that's documented, and then just grab it. But yes, I would expect the profiling software to become GCS aware and leverage it where it's there.
I'll send upstream a head up and they can fix it.
So if you're hoping to get this in Forky, then obviously I'm assuming there'll be a complete scan of the archive and rebuild bugs filed, so we can pick up on whatever needs to be done.
Yeah, so the idea is, the cool thing about this again is it shouldn't, he says, it shouldn't exacerbate any actual faults in code gen. So it'll be a case of mainly, annotation that changes. We're trying to follow a very similar pattern basically to Pack and BTI and other distros as well. There's a rather lot of packages in Debian, so we're trying to enable it in an incremental way. But what we will be doing though is with the testing we've got, we'll be testing things from GCC to make sure that everything is safe, and then we'd say this is safe because there are slight modifications to the way things like long jump, set jump work, go-to label, which is my favorite GCC feature. They all need GCS awareness in as well. So we'll be testing the base, and then it'll be documented. So.
Cool.
Just trying to understand this properly. So you showed it, the binary is not actually changing, right? But you're saying
most of it won't. So, only tiny bits potentially will. So if anyone is using anything inside GCC that manipulates control flow, So the go-to label, for example, you do go-to, and that will probably change the code gen. But most normal code that we have, I expect there wouldn't be a change.
So can we in fact just declare things as not containing anything bad? So like you say, would that be scanning the binaries for things which might be an issue? Are we just going to, are we going to actually rebuild and annotate the binaries to say yes, it's checked? I mean,
well,
how does this
part
work?
of the annotation is so this is the way the annotation works. So GCC itself will produce the assembler that's compatible. Now, the only thing that we're aware of that will make an incompatible binary is third-party assembler being linked in. That won't be annotated, and so when it's linked together, the resultant executable won't have this enabled.
Okay,
yeah.
I have a question. So when you start to activate this means a total rebuild of the architecture for all Debian packages?
Yeah, so that's why we'd naturally want to just phase it in with a natural rebuild that happens, if you see what I mean. So when we did a similar thing with pointer authentication, so when GCC 14 kicked off, the flags were in place already, the M-branch protection equals standard, and as a consequence of that, all the new packages picked it up. Now, anything that's not been rebuilt won't have this, but the idea is to try and get as much as possible to begin with, and then if there are important stragglers, address them, basically. Yeah.
Thank you.
Yeah, Peter.
Will there be any way for a Debian developer
Yeah.
to get access to a machine that actually supports this without spending a bunch of money? It's
Yeah.
so if some package I'm involved with ends up with a problem related to this, will there be any way without spending a bunch of money for me to get access to a machine that supports it so I can debug?
No, I know what you mean. At the moment, this is at the moment this is very early, so I don't actually think there's any silicon at the moment. So what we do is we're relying on the software model ourselves. The software model, whilst not being open source, it is accessible. It will execute on ARM and x86 platforms. So, for example, if one wants to play with GCS, this Yocto layer is a great way to start because it does everything for you. It downloads the model, it executes it in place, it sets the shell up for you, so you just say go. You follow that README file, and you've got a GCS environment. Now, obviously, I'm hoping there is hardware available because I'd like to buy some as well myself because I buy my own hardware as well. As and when that's available, it will be mentioned. But it's very early. The architecture's just started, so it's going to take a little while for the silicon. Yeah. But I agree with you. It's nice to have the hardware. So.
I had a related question to the remark that you said about that PAC and other thing.
Sorry? Oh, PAC and BTR, yeah.
About the rebuild, we do want to probably schedule a big rebuild in Debian for the stragglers of time T and see if there was no other things. If you know of anything that needs to be scheduled to still gain support, if it doesn't, then please let the release team know.
Thank you. Yes.
To take it
Emma
along.
and I will tag team that. Thank you. Yeah.
Anybody else? I guess we're done. Thank you very much, Steve.
Thanks.